All right, anybody have any homework questions? Okay. Well, we've been talking about the first law of thermodynamics. That says that the change in energy, usually that's just going to be the change in internal energy for us, is equal to Q minus W. In some cases, it's more helpful to use the differential form of this. And the most obvious case when you'll want to use the differential form is when you're doing calculations involving heat transfer. So heat transfer calculations, especially, let's say. We're going to want the differential form of the first law. And that looks like this. dE dt is equal to Q dot, yes?
Did you get the recording started?
I think so.
I'm good at that.
Okay, yep.
Let's make sure.
So Q dot minus W dot. And here's what all these things mean, because remember, E is a property. Q and W are not properties. They represent processes. So dE dt is the rate of change of energy and it's equal to the rate of change of kinetic energy plus the rate of change of potential energy plus the rate of change of internal energy, the one we're going to deal with the most by far. And Q dot is the rate at which energy enters the system through heat. And similarly, W dot is the rate at which energy leaves the system through work. When we use this differential form, we're going to break things up into two different types of problems. Break up problems into two types. Those are steady state. And steady state means that the properties a constant. And so therefore, dE dt is equal to 0. And then transient problems where dE dt is non-zero. In other words, the properties are changing in time, with time. Okay, well, we're going to use this most often when we're doing calculations involving heat transfer, and that's because all of the heat transfer equations have to do with Q dot. And so that just fits right into the form of the differential first law. So now we're going to talk about heat transfer. Heat transfer calculations. There are three ways heat can be transferred. Three modes of heat transfer. Those are conduction, what order do I have them in? Radiation and convection. Conduction is like when the handle of a pan gets hot. You don't have the handle directly over the fire, but as you heat up the metal on the bottom of the pan, that heats up the metal surrounding it, and little by little the whole pan becomes hot. Radiation is how we get energy from the sun. That's the only one of these three that can transfer energy through a vacuum. Everything else needs some kind of medium to transfer energy through, and it's the only reason, all of the energy on Earth is reliant on radiation from the sun. And convection is like wind chill as an example. When you, so conduction is molecules, internal energy of a molecule is vibration of the molecule. And that, as it vibrates, it starts to vibrate the things next to it. And so those molecules aren't moving across distance. They're just adding energy to the things next to them, and little by little that energy transfers. Conduction is like the actual molecules move and take that energy with. If you've ever taken an ice bath, in an ice bath, like in sports, like you get hurt or whatever, and your coach makes you take an ice bath, it's really unpleasant. But you put your foot in this like ice water, and it's super, super cold. It hurts so much. And then it sort of stops hurting. It doesn't feel so bad. And you're like, oh, I'm getting used to it. And then they come in and stir the water, and it gets super painful again. That's because your foot is in there heating up the water immediately surrounding, and so it stops feeling so bad. If you stir the water, you take that high energy water, that warmer water, move it somewhere else, move colder water back around your leg, and it's unpleasant again, which I guess is the goal. Okay, so we have calculations for each of these things, so I'm going to start with conduction. So conduction is energy transferred through a material particle to particle without the particles changing location. This requires a medium. You can't have conduction through empty space. The sun cannot transfer energy to the earth through conduction. And the formula for this is that Q dot is equal to negative kappa times A times dt dx. And I'll tell you what all of these mean. Kappa is a material property called the thermal conductivity. That's something you can just look up for different materials. A is the cross-sectional area that's perpendicular to the direction of energy flow. So that means, like, if you're talking about heat being transferred through a window, this A would be the area of the window. The energy is transferring straight through the window, and perpendicular to that is the area. It's like the amount of window that you have available for this heat to go through. So it makes sense that would be proportional. T is the temperature of the material. And at a given, you could say at a given X location, along the path of energy flow or of heat transfer. And then X is a location along the path of heat transfer. Okay, so if you have a very steep gradient in temperature, you have a much bigger heat flow. So that window is, not very thick. If our side of that window is 70 degrees Fahrenheit and the other side is 65 degrees Fahrenheit, then the rate of heat transfer is pretty small. If our side is 70 and it's negative 40, then that's a really steep temperature gradient, and so we have a real high rate of heat transfer. That makes sense. Oh, here's a little picture to indicate. So if this is the material, the medium of heat transfer, and energy is going this way. Okay, so this is the direction of Q. Then this is the area X, the area A. And X is this direction. Okay, well, let's do an example. So let's say we have a 1 meter by 1 meter pane of glass. I don't know why I drew it like that. The dimensions 1 meter by 1 meter. And on this side, let's say that it's 15 degrees Celsius. And on the other side, it's 20 degrees Celsius. The window thickness is 2 centimeters, 0.02 meters. And for this glass, let's say the coefficient of thermal conductivity is 1.05. The units are watts per meter times Kelvin. So if the temperature varies linearly through the glass, what's Q dot? Okay, so we're going to calculate Q dot, and then let's say that this is part A. But then second, I want you to notice that with all of these, the sign convention that's used for the heat transfer is not necessarily the sign, like you can't use that as the sign convention for the first law. Okay, so you have to do this calculation, understand the direction of heat transfer, and then think about how that fits into the first law. Okay, so let's say for part B, if our system is the 20 degrees Celsius side, say that's inside the house and we're interested in what's happening in the living room. What's the Q dot that you'd use for the differential first law of thermodynamics? Okay, well, varying linearly, then we know that dt dx is just 20 minus 15 divided by the change in x. O2. So that is 5 divided by 5 times 50, so 250. And so Q dot is equal to negative 1.05 times the cross-sectional area. 1 times 1 is just 1. Times 250. And so you get an answer of negative 262.5 joules per second. That negative just means that, so when I calculated this dt dx, notice that I treated it as if x is increasing as you go from the 15 side to the 20 side. Okay, that's, if you think of that as like a difference equation representing the, so our x, the way I have it, is getting bigger as the temperature increases. Well, heat transfer from conduction always goes from a high temperature to a low temperature. And so this just says that Q dot is in the opposite of the x direction. Okay. Heat is transferring in the direction of negative x. You can think about that sign convention, or it's just as easy to just think about, what direction is the heat going to transfer? It's always going to go from high temperature to low temperature, because that sign doesn't help you in the differential form of the first law anyways. Okay, so we have heat. Okay, so this is Q dot, right? So this is part A. Now for part B, our system is the 20-degree side. So is this heat transfer coming into our system or leaving our system?
Leaving our system.
Leaving our system. Going from high to low temperature. So in this case, if we're going to use the differential form of the first law, is Q dot going to be positive or negative? Negative, yep. If, on the other hand, our system was the side that was 15 degrees, energy would be coming into our system. And so that would be positive. Okay. And so every time you do these heat transfer, use these heat transfer equations, you have to think which direction is energy flowing and use that to come up with your first law sign convention. Yeah. To what? Sure. Next is radiation. Any object that's above absolute zero temperature emits radiation. This radiation is in the form of electromagnetic waves. This radiation doesn't require a medium to transfer. It doesn't require a transfer medium. And so radiation can travel through a vacuum, and that's how we get all the energy from the sun. Heat is emitted from a material according to the Stefan-Boltzmann law. And that says Q dot sub E for emitted. This is the energy that's being lost by a material, is equal to epsilon times sigma times A times T to the fourth. And the meanings of these things, epsilon is called the emissivity. That has to do with the surface of the material. It's a pure number between 0 and 1. Zero is shiny white. And 1 is matte black. So we're talking about radiation being emitted, but you know from experience what you wear in the summer, this is likely related to absorption of radiation too, because you know that if you wear matte black clothes in the hot sun, you get a lot more radiation from the sun absorbed. And it does work that way, and I'll tell you how the case where we can deal with that. Okay, the second constant is sigma. That's the Stefan-Boltzmann constant. And it has a value of 5.67 times 10 to the minus 8. And the units are watts per meter squared, Kelvin to the fourth. A is the surface area of the material. And capital T is the surface temperature of the material. All right, well, it doesn't help much in calculations to know the energy, the radiation that's being emitted, if you don't also know the radiation being absorbed. And we can't always calculate that, but there's one important case where we can. So there's one case where we can also calculate the absorption. And that is for a smaller body that's completely surrounded by a larger body. So this is like an object outside completely surrounded by the atmosphere. In that case, we can use this equation that says the net Q emitted is equal to epsilon sigma A times the quantity temperature of the body to the fourth. Sorry, that B isn't for body, it's for bigger. And the second one minus T of the smaller to the fourth. So you can see if there's a higher temperature on the net Q emitted. No, I told you that wrong again. This is the body. This is the surroundings. And you can make sense out of that because if you have net radiation emitted, that means that the body has to have a higher temperature than the surroundings. If the surroundings have a higher temperature, this comes out to be negative. Then epsilon is the emissivity of the smaller body. And A is the surface area of the smaller body. I don't have an example to do with that one, but I know later on we are going to do examples with the differential first law, so we'll get to it then. Okay, so and remember that this is the net heat emitted by the smaller body. In all of these cases, once you calculate that Q dot, you need to think about the sign and how it relates to what you've chosen as your system. Okay, none of these, you can't trust the signs on any of these for the first law. And then the last one is convection. This is when heat is carried to a new location by moving particles. The equation for this one is Q dot is equal to lowercase h times A times the quantity temperature of the body minus temperature of the fluid that's surrounding it. H in this case isn't like it's not like a first principle physics thing. It's a catch-all property that you need to measure experimentally for your special case. So it's a catch-all measured experimentally for a specific setup. A is the surface area of the body that's exposed to the fluid. So if you only have the fluid moving over one face of a cube, say, you're only dealing with the area of that one face on the cube. It's the surface area of the body that's exposed to the moving fluid. TB is the temperature of the body. And TF is the temperature of the fluid. Okay, so notice, this is important. I've already said it twice, but you can't trust any of these signs for the differential first law. So you're just going to use these equations to get a magnitude, and then you have to think about the direction that heat is flowing. All right, let's do an example. So let's say we have a gearbox. Okay, so there's one gear. And it meshes with this gear. Those are supposed to be round. The top gear is turned with a work 1. So this is the input work. And that has the effect of turning the lower gear the opposite direction. That's the output work. Call that W2. The cross-sectional area that's exposed of the outside of this box that's exposed to the air is 1 meter squared. So that's the area of the box that's exposed to the air. And the surface of the box is cooled by convection. We know that coefficient H for this convection is 0.171. That's in kilowatts per meter squared times Kelvin. And we know the temperature of the surface of the box is 300 Kelvin. And the temperature of the air is 293 Kelvin. And the last thing we know is that the absolute value of the rate of work coming in so W1 dot absolute value is 60 kilowatts. So first, we want to calculate the rate of heat transfer through convection. And second, if we assume that this is a steady state process, what's the rate of work that's delivered by the second shaft at W2? So what's W2? And this is dot. We're doing all of this as a rate. Okay, so first we're just going to use the convection equation. So Q dot is equal to, we got to be careful with the units. This H, I'm going to do everything in SI units. So this H is in kilowatts per meter squared Kelvin. So I'm going to treat this as 0.171 times 10 to the third watts per meter squared Kelvin. Times the cross-sectional area that's exposed to the air, that's just 1 meter. Times the difference in temperature. And so the rate of heat transfer is 1.197 times 10 to the third watts. Okay, so that's the energy that's leaving the gearbox due to convection. So now we can go to the differential form of the first law. It says the dE dt is equal to Q dot minus W dot. This is steady state, so dE dt is equal to 0. Q dot, so we have the magnitude of that. Is that going to be positive or negative? Well, what's our system going to be?
Our system's the gearbox. Right?
The system is the gearbox, and this energy is leaving the gearbox. So that has to be a negative Q dot. Okay, so 0 is equal to negative 1.197 times 10 to the third. And now for our work, well, we have two sources of, two places where energy is transferred through work. The first one is that W1, and that's the one that we're given. So is our system at W1, is our system doing work or having work done to it? Is work being added to our system or removed from our system?
Work is added.
Work is added to the system there. So is that W dot positive or negative?
That'd be positive.
Any other guesses? Yeah, negative. Right. Because, so remember, positive Q is energy coming in. Positive W is energy going out.
Okay, yeah.
Okay. So, so this is negative, what did I say? 60 kilowatts. So that's 60 times 10 to the third watts. And then what about W2? Do we expect that to be?
That one then should be positive.
That's right, that one's positive. And that's dot differential form. So we have 0 is equal to negative 1.197 times 10 to the third plus 60 times 10 to the third minus W2 dot. If we did our signs right, this W2 dot should come out positive. And so W2 dot is equal to 58.80 times 10 to the third watts. Anybody have any questions about that? All right, well, with the same equations, there's no, you can solve for the same number of variables, whatever those variables are. So I have another example that's sort of similar to this, but instead of being given the temperatures, we're going to use it to calculate the temperature of one of these things, which is something that could be useful in an engineering application. If you're worried about something melting or whatever, you can calculate the energy transfer and use that to deduce the temperature. Okay, so in this example, we have a chip, a computer chip, that's embedded in another material. So only one surface of this chip is exposed to the coolant fluid. The area of the exposed part of the chip is 5 millimeters by 5 millimeters. This coolant is taking energy away from the chip by convection again. And we know that H is 150. And that's in SI units, watts per meter squared Kelvin. This is all steady state, and we can measure the temperature of the coolant. And the coolant temperature is 20 degrees. And we want to know what's the temperature of the chip surface. Okay, well, We're not going to solve for the same variable we did before, but we have the same system of equations to solve. So let's first look at the equation for convection. So Q dot is equal to 150 times, in SI units, this is 25 times 10 to the minus 6. That's the area that's exposed. And then the temperature, we have, I'll call it T sub C for the temperature of the chip, minus 20 degrees. And if you multiply that out, you get a Q dot that's equal to 0.00375 TC minus 0.075.
And in this case, there's no work being done in the system?
There is, because I forgot to write it though. That's important. So the work that's being done is electrical work that's being delivered to the circuit. So the electric power, I'm going to fit it in here so it looks like I did this from the start. The electric power going to the chip is 0.225 watts. The coolant temp is in Celsius. For the convection, for convection and conduction, both, you can do these calculations in Celsius because you're just talking about differences. For radiation, you need to have it in Kelvin because of the fourth power. So for this, we won't have to convert. We can just do all the calculations in Celsius. Okay. So this TC, when we calculate it, is going to come out in Celsius. Okay, that's Q dot. The chip is going to be a higher temperature than the coolant. So this is going to come out to be a positive number. Okay, so now we have to think of the sign convention of the first law. A positive Q means energy is going into the system, into the chip. Okay, what's happening here? Is energy going into the chip or leaving the chip?
Leaving the chip?
Leaving, so this needs to be negative. Okay, so I'll write this as an absolute value, but for the first law, we need this Q dot to be negative. So I'll write that as 0.075 minus 0.00375 TC. Everyone with me on the sign convention on that? Anytime you use heat transfer equations with the first law, you're going to have to think about the direction of heat transfer and deal with the sign convention. Okay, so now we can go to the first law. dE dt is equal to Q dot, so that's what we just calculated, minus W dot. Positive W dot would be the chip doing work on the surroundings. What do we have in this case? That's right. And so this also needs to be negative. This is steady state, so dE dt is equal to 0. And so 0 is equal to 0.075 plus 0.225 minus 0.00375 Tc. And so Tc is equal to 80 degrees Celsius. Any questions about that? Okay, well, so that's the end of the first law. I think I'm going to stop there and start next time with properties of simple compressible substances. So we'll be talking about, we'll start getting into using property tables, the ideal gas law, and the PVT surface and graphs and things like that. So we've been talking about using the first law for processes. Now we're going to start talking about, for certain materials, what do we know about the different properties at a single state, equations of state. So if we know pressure and volume, can we figure out something about temperature, that kind of stuff. Okay, that's all. Have a good weekend. And yeah, if you want to talk over Zoom, send me an email and we'll set up a time. And also I have office hours in the tutoring center tomorrow from 10 to 11:30.